Hello to everyone, my name is Arman, and today I'm going to present our research work, a research paper that we call method name prediction for automatically generated unit tests. So there exists a range of tools of automatic unit test generation, as Runloop and EverSuite. They automatically create unit tests for classes, methods, and in unit test format. The main goal of such tools is to generate unit test suite, which will execute as many as possible computation paths of method under test. So these after-generated tests are often used in areas where it's mandatory to cover all lines of code with tests. They are quite effective at exposing at unexpected scenario in code. I also want to add first, I forgot to add that we have all this work are related to Java language. So analysis and topic discussion are related to Java language itself. So one of the main challenges of these tools of automatically unit test generation is incomprehensible unit test names. The tests are usually abbreviated as unit test 1, unit test 2, and 3, and etc. Potentially, tools can generate a large number of tests, sometimes a dozen tests for one unit test, and each of these unit tests will trigger a particular behavior of the meta test. We call basically each execution of computation path we call triggering a behavior in the method. So every test will have a different. Every unit test will trigger a different code behavior in the method under test. We believe that the name of such unit tests have to reflect the behavior it triggers, so that developers could easily understand grasp what the unit test testing without looking at the code, at generated code. So we decided to use deep learning techniques to generate Java unit test name, which will reflect triggering behavior in its name. So the goal we put to our neural network to analyze each unit test structure, find its corresponding name. And the name have to capture the, as I said, the idea of what's triggering in the method under test. So basically, approach is to represent structural information. Our approach is to represent structural information of the code as syntax tree in graph neural network. While graph neural network is connectionless models that capture dependencies of the graph via message passing between nodes of graphs. In encoder-decoder architecture, graph neural networks are usually used as the encoding part, and while as decoder, recurrent neural networks are usually very popular. So basically, we feed our syntax tree as the graph to graph neural network. Then graph neural network will pass some encoded embedding of this graph to recurrent neural networks, which will then try to decode embedding into a sequence of tokens, which is the name. So we choose to use open source projects as a dataset because software engineers naturally name the unit test based on the functionality they are testing. The body unit test carries only setup and assertion information, while code behavior is triggered in a called function. So, for example, a developer can create a dozen of unit tests for one function, and each unit test will have a different name. So different code behavior in the method under test. So we believe that's why unit tests. So that's why unit tests will have different names that reflects this. What this engineers is trying to test, and to capture. So that's why we decided that well-written open source projects with unit tests are well suited for training neural networks to predict name. We choose open source projects with the highest star counts. For dataset, we chose the fetch projects with the highest number of appraisals, as they are most likely to follow best practices of code naming. This way, we acquired about 1,000 repositories with the highest star counts. But after analysis of downloaded unit tests and GNNs, we developed a list of criteria to filter out the test functions. In order, our model will learn only comprehensible function names. So we applied following criteria. First is that method name must contain no more than 5 words, excluding the word test. So because many of the tests in the data set have long names which were difficult to read and to understand. To avoid such a long name generation, we put such a filter. Method name must include at least one word. Some of the test names consist of only nouns and pronouns. As a result, the names lack it of description of actions, what is triggering. Then we put another criteria is that method of unit test must contain at least 4 lines of code, because 2 or 3 lines of code are little informative and have little difference from other unit tests. So after filtering, we had a data set where the average number of tokens in each name were almost 4 words. To extract a graph from source file, we perform following steps. Steps 1, 2, 3 are very popular, very similar to other research works that are doing in this field. So we basically extracted abstract syntax tree from source file that contains unit test. Semantic edges of data flow and control flow between variables are added to that abstract syntax tree. Then a subgraph related to unit test body, and unit test body is cut from abstract syntax tree. On step 4, we have added new edges to control flow to abstract syntax tree between the upper nodes. And on step 5, we identify what method is called from unit test. So we identify what's the using call graph, we identify what the methods are called and connect to graphs, unit test graph and call graph into one giant graph. Steps 4 and 5 are performed using suit framework, and instead extraction was performed using Java parser. So here's an example of sample structure that we feed our neural network. Is above its unit test with the call it function. You see that unit tests have description of setups of variables that num is equal 10. Then there is call function and assert. Based on, and we also have information about what the method is called based on call graph. And we build abstract syntax tree and connect 2 graph into one. So the unit test graph and call it method graph using call graph this way. And this is our basically graph of unit test that we feed to our neural network. We use a graph neural network. It's actually a gated graph neural network that can capture relations between nodes. It basically, when we feed our abstract syntax tree to that neural network, it will resemble this whole model, but resemble whole model of graph. And during training, it will send messages from one node to another. And during training, we can iterate multiple times to send a message from one node to another node based on edges we have. And after after a certain amount of iteration, we will every node will have information about neighboring node and about neighboring nodes. And different color of these nodes depicts a different type of nodes. There is also different edges, types of edges. So we, on top of our graph neural network, we have implemented our attention layer that will divide our nodes into different set of node types. Each set of node types represent one particular type of node types. We did it because some of the node types don't have any information. They're very repetitive. Some of them are very empty, always empty, and some of them are very rich, as they could have information about identifiers, about names, variable features, etc. So we divided that node types into different set, and each set we will put into, for each set we will put some attention mechanism. So in the middle of the of my presentation, you can see mechanism that we developed for attention node type, for our node types. It will divide into groups of node types, then calculate how much important each of them for names prediction, and then encode to one layer inside. Then we use our as a decoder a simple recurrent neural network. It's actually vanilla recurrent neural network because it's because our sequence of tokens are very small, like 4 or 5. So we decided to use only vanilla network, and in our experiments it showed very good results also. So basically it consists of 2 layers, hidden layer and output layer, and hidden layer is used as a sampling strategy to predict current token, and as a feedback to predict next token. For comparison of our approach, we took code-to-sec and graph neural network based on LSTM that are very widely used for this task and can be considered as state of the art. So code-to-sec, it's predicts functionally based on abstract syntax tree representation as our model. It also follows standard encoder-decoder architecture. It decomposes abstract syntax tree into a set of paths where each path is encoded to vector using LSTM. And inside it also uses attention mechanism and LSTM to predict a sequence of tokens. GNN and LSTM uses also similar to our approach, but the attention mechanism is put to all nodes in the graph, and based on this, it tries to identify important nodes. So as you can see on the graph, our method is very outperforms our other approaches far early and far above. Like on 21st epoch, it's already reached 37% in accuracy. And and according to the table, our model is superior to other models in precision recall and F1 score. And below you can also look at the sample of predicted example with our approach. And so on the right side, there's a figure that depicts the attention score for different type of node types. It's in ranking. These scores were calculated on validation set. According to this ranking, our neural network puts high importance on the nodes that have links between unit tests and method under tests, and keep some token parameter identifiers. We also find out that our model have very good prediction result on the graphs that very rich in nodes that have at least 25 unique node types. We believe because when a unit test executes a called method, it puts high importance to on unit test method body itself, on the what's the setup in the unit test body and what the assertion was in the unit test body, and based on this information it tries to it can infer what behavior is triggering and testing on the called function. And when we have reached such unit test body, our approach will give a very good result, almost 70% accuracy in prediction. As the future work, we intend to incorporate information about trace execution with depiction of nodes order execution. We believe that program traces could bolster our results in name prediction. We have, so to sum up, we have developed data preparation and preprocessing for Java unit tests. Sorry, the test body. And based on this information, it tries to, and our implementation of neural networks for the task of Java unit test name. Our proposed approach showed very good results and competitive to other state-of-the-art models. So we also put our models on open source. So there is a link on GitHub where you can find our link in our paper where you can find our code with documentation and experiments results. Thank you very much. Feel free to ask questions.
Yeah, it's really interesting, impressive. I feel practical need for this tool, definitely. I have a question about validation. Maybe I missed that from the presentation. So how exactly did you validate and calculate the accuracy and precision? So what was the test data set? What was the validation data set?
So we had dozens of, we have fetched thousands of repositories in GitHub with a very high appraisals, and we, after filtering, we divide our data set into 3 groups: test and validation and test set, and we randomly divided into that categories and then trained on training set and and tested on test set and validated on validation set. I want to point out that whenever we would use a random divide unit test set by not looking at the project itself, then our results will go up to 60–70% because neural network will train on the project names, and usually project names have in one project unit tests have very similar test names. But whenever we divide randomly, not looking at the project itself, then the overall overall prediction quality drops, because the versatility of the names will increase in the data set.
Interesting. But for you, your prediction, the method name you predict has to literally, letter by letter, match the actual method name. And in this case, you believe this is a match, right?
We use tokenization, so we divided names into tokens, so words, and we developed our algorithm that will check for matching every word to word. So whenever there is one word is not accurate, we will give like, okay, if it's one word out of 5 words is not incorrect, then we will say, okay, it's 80% accuracy.
So can you move to the next slide? I think you have an example for that. Yeah, so if you look at this table on the left bottom corner, then I see the prediction, for example, first line, it says should place service, but the actual name was should place blank sub process. So in this case, is it a match for you or it's not a match?
Only it will be like maybe I think 20% accuracy, will say, but you will see that service and subs process are very similar to each other. They are I will put into one semantic category, so it's actually like it's enough for research, but for production it still seems like have to be investigate more because it's still unpredictable sometimes. But overall, it will try to give words that are very similar in semantics. Because we have a very big data set, it will see that after services and sub-processes are usually interchangeable and process services. And you will see that sometimes it will put instead of word config, it will put the word configure. It's an error, but if we look on the other side from semantic perspective, it's actually more or less likely. But of course, there have to be more work done on investigation on this from NLP point of view, from natural language processing point of view.
And did you try to do this training in this way? You train your model on one set of projects, and then you validate your model on a completely different set of projects, not set of methods, which are randomly mixed with from different projects, but use one set of projects for training and completely different set of projects for validation.
Oh, okay. If we will do that, then, for example, if a training set is small, like hundreds of projects, and test set is 10 projects, and they're not completely related. For example, 100 is a web projects, and another 10 projects is the Android projects. Then the test names will be, the results will be very low, I will say, because they have very different domains. So that's why you have to mix it in training set, everyone randomly choose a training set, test set, validation set, randomly. So different domains will be mixed up. Of course, if you will create a training set based on the web projects and then test on the web projects, it's the same domain and the testing words are very similar, and our prediction result will go up, like will skyrocket. I mean,
right. So it seems that to make this tool useful for production usage, it's better to first train it in my project, for example, and then use it in my project for automated test name generation, right? That would be the best usage scenario.
And for neural network, it will be not enough, maybe a data set, but there are other methods like rule-based, which can be applied like this. Rule-based, where you have very small data set of your own history, and you have, of course, it can be mixed differently, but it's possible then, yes. But it's you have to have like a data set of your data of your project. But if someone comes without any experience, then it will be a different story.
Can you move one slide left? I have another question. The previous, left, before, yeah, up. Yeah, one more. Earlier. One more. Yes, this one. So this one with the graphs. Yeah, this one. So here you're saying that you are looking at the test and at the body of the test, and you see the calling of the method is positive, and then you go to the production code, you find this is positive method, and you take the graph from there, the AST from there, and then you inject it into the main graph. But do you do it recursively? Do you go, if you find some other call in the production method, do you go recursively deeper and deeper?
We have a boundary of depth of 1. We can go up inside because it will raise cycles inside of it. So it's very problematic in that way. It's enough for us to look what method was called in this structure. most information are in the unit test itself, because sometimes we have 10 unit tests that are calling one function. So so call function is the same for everyone, but information that we are interested is in the unit test itself. So we are mostly interested in the unit test, what the test is calling and what it's set up and what's the assertion. And based on this, give a prediction of what the behavior is trying to test and capture. So
makes sense. Because I was thinking you were doing this recursively, and my question was, how deep do you gonna go?
It will arise the main problem if you go up. It's the recycle. It could go into a cycle first. Another one, it will increase our data examples to thousand nodes, and our neural network will just will die. I mean, there is, even in our example, some unit tests have thousands of nodes inside. For neural network, it's very difficult to grasp all information and connection inside of it. But if you will go inside of what's called and try to inject everything, our neural network will just go down with accuracy.
Did you try to somehow validate your result against the human intuition? Maybe show these method names to people and ask them what they think, whether the names actually make sense?
We're actually trying to. We are working on this project. We are continuing this project with. We are adding right now execution paths. Not only so each unit test what will trigger inside of method, what's inside method, and what's the execution path. And based on this, are creating a predicted name, and we are we're injecting into product right now. So, and based on this, we will get a review result. Then we will publish another paper with this information.
Sounds interesting. Yeah. Because maybe I'm just thinking maybe the machine is right according to the previous results, but maybe the people may think differently, and their names could be different.
It's maybe yes, it's maybe like it was trained on correct set maybe and tested on. It's quite possible, and the names. I would say it's another big research where we have to have independent researcher from not our company but other companies, and it's have to be very representative in number, so to get the very valid results.
Okay, one last question. How much time did you spend on this project approximately?
On this project there were like 3 persons working, 3 sometimes 4, and we spent like 8 months up to, because most of the time we have spent on data collection, on filtering criteria, analyzing the names, etc. So it took like 70% of time, and training testing it took like a month and a half.
Okay. It's a big project.
Yeah, it's a data set. The problem was to collect and get a good data set and filter out good results that good data sets that could be helpful for our text generation.
Okay, thank you very much. Thanks for submitting.
Thank you very much.
I hope you will consider us next year, and bye-bye.
Thank you very much. Bye.